Okay, it's my pleasure to introduce Ben Asher for today's seminar. And he's a graduate student at Florida State University with Dr. Sergio Almaraz-Calderon. He studies fusion reactions using radioactive ion beams and Encore, a multi-sampling ionization chamber that he also designed, built, and characterized. He's also been an integral part of the development of isomeric beams, as well as CATRiNA. In recognition of his contributions, Ben received the John D. Fox Award in 2020 for his excellent work, willingness to help, and expertise around the laboratory. So with that, I am going to pass over to Ben. Thank you.
Well, hello, everybody, and thank you for that wonderful introduction. As she said, my name is Ben Asher. I'm a graduate student at Florida State University. And I'd like to thank you all for coming out to hear me talk today, as well as the committee for accepting my abstract to give me a chance to talk about one of my research projects here. More specifically, as was mentioned, the Encore active target detector and my measurement of 17 fluorine plus 12 carbon fusion that was done with it. So first, just a brief outline of my talk today. I'll first start off with some basics of fusion and some motivation as to why we measure this process, as well, and specifically to loosely bound light nuclei, which 17 fluorine is. I'll then give a brief history of 17 fluorine, as well as some other measurements of fusion that have been done with this. Then I'll give a pretty detailed look at my detector. And finally, I'll show you the results that I have, as well as some conclusions we can take away from it. So starting right off, why should we study this process? Well, a lot of this started off with the search for the island of stability and super heavy elements, meaning smashing heavy things together to find even heavier things. It's also very important in nuclear astrophysics, particularly as you move well below the the Coulomb barrier and into the gamma window. The most famous examples of which are carbon and oxygen burning. However, to better understand this barrier, it's important to measure at energies around it and with different nuclei that might introduce dynamic and static effects that test our understanding of the fusion process. And in particular, light excited nuclei and halo nuclei that have very unique structures further push our understanding of this process. So what is this process? Well, quite simply, it's a process in which two nuclei form a single compound nucleus. And what I have here on the right is a very crude drawing of this process with a potential, your nuclear attractive potential with your Coulomb repulsive potential, and in principle, your angular momentum as well. This is characterized by a few terms, namely the potential energy of the barrier VB, or how tall it is, the barrier radius, how wide this well is, and h bar omega, which is the barrier curvature, or effectively how thick this wall is. These terms are very important as you can extract them from whatever calculation or analysis you use of your system, and then use them to compare them to systems that might be similar, as well as compare your models and calculations. But no matter how this process is done, once it reaches a bound state, it will be in some excited state, which then reaches equilibrium through different channels, shooting out protons, neutrons, alphas, gamma rays, leaving behind what's called an evaporation residue, which is how we typically measure this process experimentally. So how do we measure this process? Typically, it's with some sort of delta E partial energy measurement with a total energy measurement in order to parse out the A and the Z of whatever is coming out the other side of your target, since an evaporation residue will have a higher A and Z than any other reaction that happens. You can also measure the light particles that I mentioned and can be in coincidence with gamma rays, particularly if you want to push well below the Coulomb barrier and clean up some of your background. In principle, if your evaporation residue is of high enough mass, you can also measure the fission fragments if it undergoes fission. However, with all these ways of measuring, I argue that they're not efficient, both in detection and beam time. And to expand on what I mean by that is just a few issues that happen with any fusion measurement that you're trying to do. Most important of which is beam normalization, or how well you understand your beam. since the measurement of fusion is essentially a probability of how many evaporation residues you get with how much beam you're pumping in. You can, of course, try to increase your statistics by putting more beam in. However, as we move away from stability and into low intensity beams, that might no longer be a luxury. On top of that, with a lot of silicon measurements, say, you're only measuring a certain amount of angle. And if you want to assign an absolute cross-section to your fusion, then you need to account for the full solid angle, which can become model dependent. And the reason I bring these up is because I want to argue a different way to measure this, and that is with active targets. These are detectors, quite simply, where the gas in them is both the detector and target, and they've been developed around the world. This is just a list of a few, such as TechSat at TMU, Anison here at Florida State in collaboration with LSU, Tactic, Maya, all the TBCs being developed, and my unbiased personal favorites, Music and Encore. And these address some of the issues I raised before. At least in Music and Encore's case, they are very efficient, meaning they cover all your relevant lab angles. And you can understand your beam very well since it counts the beam for you. On top of that, as we lose intensity and into more interesting systems, you want to measure a large range of energy with the precious beam time that has been given to you. And these, with the energy loss as the beam goes through these detectors, offer a wide range of energy sampling. And the inherent low beam acceptance of a lot of these detectors, since in principle their ionization chambers, are perfect for low intensity beams as we move further away from stability and into the land of loosely bound and halo nuclei, which is what 17-fluorine is. So what are these exactly? Well, they have an extended density distribution, meaning they're larger than they should be, leading to large interaction cross sections. On top of that, since they're loosely bound, they have a low breakup threshold, which can affect your fusion measurement and have an effect on transfer, which is outside of the scope of this talk. This immediately has some very important implications in the fusion process, namely with their extended size, you might think that since cross-section scales with the size of the nucleus, then if you have an abnormally large nucleus, then you'll have a higher fusion probability, effectively widening your well. However, on the other side of things, with a low breakup threshold, the Coulomb barrier might be enough to break up the nucleus and never giving it a chance to fuse in the first place. And just to give a few examples of how this works with these nuclei, I'll start on the neutron side of things. The most famous example is probably lithium. What I have here on the left is some work done where they measured 11 lithium on 208 lead, shown here, and they measured the total fusion cross-section of the system. They then compared it to a 1D barrier penetration model and showed that there is a lot of suppression well above the barrier in both of these simple examples. They then went one step further and did a couple channels approach, which essentially just adds excited states of these nuclei to try to account for this, and still showed that there is quite a lot of suppression above. For neutron halo nuclei in general, this is actually kind of a feature across the board for these and has since been attributed to the breakup in these energy regions. On the other side of things, with proton-halo nuclei, there's not a lot of data. 8-boron is really the only one measured, and the results are a bit inconclusive. What I have here on the right are the two measurements done with it, one on nickel and one on silicon, and they're reduced by these potential terms from earlier to try to compare the two. And what they found was that if you measured 8-boron on 28 silicon, that there was some slight suppression above the barrier, which in this case would be at 0. And in 58 nickel, they showed quite an enhancement. So more data needs to be in general for 8-boron and proton-halo nuclei in general to get some sort of systematic comparison. More data is needed. And just to throw out there, there was a recent measurement just put out a few days ago where they did a boron on 40 argon. However, I didn't have a chance to include it in this talk, though I believe it agrees with the 28 silicon case. So that brings me to 17 fluorine. 17 fluorine is a proton dripline nucleus that is loosely bound. Its ground state is a D5 and its halo nature is a little bit up for debate. However, its low-lying first excited state is a halo state and lies just below the proton separation energy. On top of that, it's a relatively easy beam to make. And I point that out because one reason there's not a lot of data on the proton side of things is because these beams are hard to make. It's like 8 boron here and 17 neon is another one. So 17 fluorine gives us a good jumping off point to try to understand the systematics of these type of nuclei. This is not a new thought of 17 fluorine might looking weird in fusion. It has been measured before, first on 208 lead at Argonne National Lab. And what I have here on the right are the results. In the closed circles are their 17 fluorine on lead measurement, and in the open circles is their 19 fluorine on lead measurement. And in the dashed line is a 16 oxygen plus lead calculation that is then shifted by 9/8 or the ratio of their charge. And what they concluded was that 17 fluorine looks just like 16 oxygen fusion, which was perhaps surprising since the thought was this extra proton, the enhanced radius from the extra proton would lower the barrier and thus increase your probability of fusion. On the other side of things, they looked at 19 fluorine and said that above the barrier, it looks more or less the same, but as you go further down in energy, there seems to be some suppression. This is perhaps not surprising, as an idea was put forth of a polarization or shielding effect that might happen with these nuclei. So if you think of 17 fluorine as a 16 oxygen plus a proton, then as this nucleus flies towards the lead, the proton will then polarize the other side and be shielded from the lead. Thus, the fusion you're really measuring is then just 16 oxygen onto 208 lead, and thus the fusion looks similar. Moving on was a very recent measurement done on 58 nickel, where they measured total reaction cross-section, total fusion, as well as a few breakup channels, I believe. And what I have here on the right are their results, where in the stars, they extracted a cross-section from both proton evaporation and alpha evaporation, meaning they measured the light particle in backwards angles and extracted a total fusion cross-section. And what they found was something similar, that if you compare it to 16 oxygen, then it looks exactly the same above the barrier, but they're 1 point below, it seems to show some sort of enhancement. And this leads us to 12 carbon. So what we aimed to do with this measurement was have a low Z target, thus reducing any sort of polarization effect that may or may not happen, as well as any sort of breakup effect that might happen. On top of that, really nailed down whether this D5 state has any effect on the 12 carbon, and look at coupling to the 1/2 plus halo state and see if there's any effect on fusion. On top of that, we wanted a large above barrier energy range, meaning not just measure a few points, but really kind of everything above the barrier to get a really clear picture of what might be going on with this nucleus. And with adding 12 carbon with the nickel and the lead, we now have complete systematics of a large range of mass and a large range of Z, thus leading us to the first radioactive beam experiment with the detector Encore. So what is Encore? Well, it is a multi-sampling ionization chamber, or MUSIC. And MUSIC is a detector that was developed at Argonne National Lab specifically for measuring the fusion of carbon isotopes. It is 100% efficient, meaning it covers all your angles. It is self-normalizing, meaning it counts the beam for you. And on top of that, the analysis is relatively simple. So with their detector, they measured the carbon isotopes, as I mentioned before, namely 10 carbon, 12 carbon, 13 carbon, 14 carbon, and 15 carbon, primarily to find the S factor for stellar nucleosynthesis and X-ray superburst. They also took a little bit of a look at this unique systematics they had of neutron deficient to neutron rich of these isotopes, and showed a clear trend in increasing cross-section as you put more neutrons on and compare it to some models. So with those wonderful results in mind, my advisor, Sergio, came down from Argonne National Lab to Florida State University and tasked me with building one of our own to use here at Florida State University. And this detector has been a very large part of my work and has been now a significant chunk of my life, as you can see from the varying lengths of hair and beard, as well as a mask from a large experimental campaign we carried out last year. The nitty-gritty details of putting this detector together are not important for this talk. However, I am more than happy to answer any questions about it, either later on or through email. But what is important is how this detector works. So here is a SolidWorks schematic of the field cage with the real field cage. And when we're working on it, we kind of use the top as a table. So when it's inside the detector, it's flipped upside down. So the way this works is with an aluminum cathode at the bottom that is negatively biased to over 1,000 volts, depending on the settings. The anode is then, in my case, grounded, creating an electric field that is perpendicular to the beam axis. This chamber is then filled with gas that is slowly brought in and out through these gas ports here in order to maintain the gas to be fully quenched. So the beam comes in through this little window that I cut in the field cage and into this active region that is filled with gas. The beam then will deposit energy as it passes through and then ionizes the gas. The free electrons can then move along this electric field and up to the anode, where they are then collected. The charge of which you read is then proportional to the energy loss of the beam, or in principle, any particle that passes through this active region. So the anode is really where a lot of this magic happens. It is a heavily segmented anode in 18 strips. We label 0 to 17. The middle 16 of which are segmented into left and right in this staggering motion, where the beam is then tuned such that it passes right through this segmentation. 0 and 17 are not segmented and are what we call control strips that we use for counting, vetoing, dating, or what have you. The left and right can then be added back in analysis, which will be very important in a second. So as I mentioned before, the beam comes into the detector and begins to lose energy as it passes through. The segmentation of the strip then gives us a delta E measurement over every strip, effectively giving us a sampling of the Bragg curve as the beam comes through. And what I have plotted here is a 16 oxygen beam coming through my detector that then imparts its Bragg peak in strip 16 and then dies into strip 17, where you see the beam blow up. This, as I mentioned, we hit a delta E in every measurement. So what is important is if I were to look at a strip and a reaction were to happen, then suddenly you have a higher particle of higher A and higher Z, which will then lose even more energy than the beam, effectively starting a Bragg curve well above this, and then stop in the gas well before the beam ever does. And this gives us our first two conditions in order to find an evaporation residue. So I'll start off, I'm going to walk you through some of the analysis just to make it clear on what exactly I'm measuring here. So I'll start with beam events. So as I said before, The beam is tuned such that it goes right through this staggered segmentation. And what I have plotted here in red is exactly the Bragg curve I showed you before, just normalized to channel 500 to make life a little easier. What's in blue and green is the left and right of each segment. So if the beam is traveling straight through, then in strip 1, it will only be seen by the left side. And in the next strip, it'll be the right side, and so on and so forth, showing that the beam travels straight on through. As I said before, if a reaction were to happen, suddenly you will have something of a higher A and a higher Z, effectively starting its own Bragg curve, which then dies well before the beam ever does. So in this case, we're looking at a reaction inside of strip 5. So it looks like beam as it comes through, imparts energy, and then goes on its Bragg curve. Now, the reason I know this is an evaporation residue and thus a fusion event is we are not sensitive to the light particles. So we set our gains and settings such that we aren't sensitive to protons or alphas. So we are only looking for heavy nuclei. So a reaction happens, and I know this is a single heavy nucleus since it stays with this staggered pattern, meaning it's a single nucleus going along the beam axis. In the bottom panel here, I have a high angle fusion event. So in strip 5, and it follows a similar path overall. So delta E spike in strip 5, and then finally dying well before the beam ever does. I know it's high angle and evaporation residue, again, since only the left side fires, thus we don't see anything in the right side, which for a scattering event would be needed kinematically. And to show you what I mean, on the right here, I have our typical background or scattering events where the overall energy loss follows a similar trend with a delta E spike and then dying well before the beam ever does. However, I know there's 2 heavy particles indicating scattering because both sides of the detector fire. The blue and the green fire for some time until whatever's on the right side either stops in the gas or exits the active region. We can then throw out any of these results and begin to calculate fusion. So guided by some Monte Carlo simulations, I have an algorithm that does this for every strip. So I showed you a specific example in strip 5, and this gives us an energy or a point for each of these strips. And so we can then immediately find our fusion probability, meaning I just count up everything that looks like an evaporation residue, and then I count up all the beam that we're pumping into that strip. And then in order to assign an absolute cross-section, then all we need to do is calculate the density of the gas, which we know based on a very high precision gas monitoring system in the detector. The next very important step is then how you assign an energy to this point. So what I haven't mentioned is in the back of the detector is a silicon detector that we can measure the beam directly and measures the beam as we fill it up with gas to understand how the energy of the beam is lost as it passes through the gas. I should mention that at typical operational pressures, the beam dies well before ever reaching the silicon detector, but it gives us a very good place to start. We then calculate the energy in each strip by least, assume the reaction happens in the middle of the strip, thus giving us an energy average of the cross-section over the thickness of the strip, therefore, which I then report as my energy error. So with that in mind, with all that analysis in mind, we now can do experiments and find cross-sections. So we started with 19 fluorine and 16 oxygen, which we have the ability to do here at John D. Fox with the tandem accelerator that's virtually behind me. Starting on the right here is the 19 fluorine stable beam results, which is not quite as well studied. However, we reproduced the published data within error. On the left side is 16 oxygen plus 12 carbon, which has been studied a million times. And again, we reproduced the data quite well even catching some of the oscillations that are known to happen within the system. So with a decent handling on the stable beam, it's time to do a radioactive beam experiment, which again, we have the capability of doing here at FSU. So in the John D. Fox lab, we have the 9 megavolt tandem accelerator, which can then boost a beam and immediately be kicked off to the left here in what we call target room 1, where we do a lot of stable beam experiments, including the 19 fluorine that I showed to you before. In the case of the 17 fluorine experiment, we started with 16 oxygen that was boosted to 64.5 MeV, then into the coupled linear accelerator we have to further boost it to 91.5 MeV, and then finally deliver it to Resolute, which is our radioactive beam facility, where we had a cooled deuterium gas target inducing the DN reaction to then produce 17 fluorine radioactive beam out the other side. Where at the end of this beam line, we put the detector Encore, which we then filled up with 168 torr of methane or CH4 gas. So in this case, the carbon is the target. And just to keep in mind, we don't see any reactions that happen with the hydrogen. And with this pressure, we then scan an entire range of, in the center of mass, of about 8 to 20 MeV or so. So the 17 fluorine arrives at my detector with 16 oxygen in tow. Now these differ by only 1Z and 1A, thus is pretty hard to separate within my detector, though not impossible. So we further separate out by time of flight, which we measure effectively from the production target to right after what's labeled solenoid 2 here is where Encore was, or my detector. We then couple that with the delta E channel of the first control strip, or strip 0, and get separation of the beam. Now, it's important that both these beams come together, since the 16 oxygen then provides a benchmark for the analysis procedure that I showed you before. Both beams come at about 1 kilohertz or so, 17 fluorine slightly less. However, with the efficiency of these detectors, the entire cross-section that I will show you was done in just a couple of days. So without further ado, I want to give a quick overview of reduced units, since these are very important when you start to analyze your results. As I mentioned way back at the beginning of the talk, with your however you model the system or calculate the system, you can extract a barrier radius, a barrier potential, and a barrier curvature. And using these units, you can then compare your system to other systems. So in my case, I have 17 fluorine, which you can think of as a 16 oxygen plus proton. So you might want to compare it to 16 oxygen. On the other hand, 19 fluorine is the stable isotope of this. So you might want to compare 17 fluorine to 19 fluorine and really nail down if anything is acting strangely, essentially. So what I have here boxed off in red is sort of the original way to do this, where you normalize by the barrier radius and barrier potential. And I'd say this works well for well-behaved systems, meaning if you have a halo nucleus, then your barrier radius might be over-exaggerated anyway, and you might lose some insight into what you're looking at. What I have boxed off in blue here is a completely model-independent way of doing this, though it does have some issues of its own. However, it's good for above barrier and close in A and Z. So in my case, I have 17 fluorine, 16 oxygen, and 19 fluorine, which are all close and all done on 12 carbon. Therefore, this is the reduction procedure that I will choose to show my results. And what's boxed off in green here, I will also come back to later, is the universal fusion function, which is great for, which is essentially an interpretation of the 1D barrier penetration model, and is good for comparing over a large range of A and Z. However, it does reintroduce some model dependency through this barrier radius, barrier potential, and the curvature. And as I mentioned, it's good for a large range of A and Z. Say if you have 17 fluorine that has now been measured on 12 carbon, 58 nickel, and 208 lead. But first, my results. Here I have plotted my 17 fluorine plus 12 carbon fusion and my 16 oxygen plus 12 carbon fusion, both measured simultaneously within my detector. On the y-axis here, we have these reduced units as I briefly explained before. And on the x-axis, I have reduced the energy in this in order to remove any sort of inherent geometrical effects of these nuclei. What is also shown here are curves that were calculated in collaboration with Nicholas Keeley at the National Center for Nuclear Research in Poland, where he took a M3Y double-folded potential, meaning essentially that it's a calculation and not a fit. And as you can see here, the experimental data above, well above the barrier seems to agree quite well. As you go towards the barrier, which I have our extracted barrier labeled in the arrows here, there is some slight discrepancy. However, it's well within the energy resolution of this detector. This is now in agreement with the lead and the nickel measurement that was done before. On the other side of things, we now have a 19 fluorine data set that we can compare to using the same detector. Again, on the y-axis is plotted the cross-section of these reduced units and the energy similarly. The black is the 17 fluorine as I showed before, and the curve is the exact same. And now in the red triangles, we have 19 fluorine above barrier measurement. Again, in collaboration with Nick Keeley, we did a calculation using Frisco and showed that the experimental data agrees quite well above the barrier as well as the calculation. Once again, a small discrepancy as you approach the barrier, however, again, well within the error bars of the detector, which is in qualitative agreement with the measurement on lead. So with all that in mind, I just showed that 17 fluorine looks like 16 oxygen and it looks like 19 fluorine, but we were hoping to see that this 1/2 excited state would have some sort of effect. So again, we turn to Fresco where we can then add a couple channels. And what I have plotted here are then the cross sections broken down by those channels. More specifically, the green here is that 17 fluorine 1/2 plus halo state that is shown to be an order of magnitude below the total cross section, indicating that, again, it has no effect on the fusion in this region. However, at deep subbarrier regions, more measurements are probably needed because there might be some effect. So with my 12 carbon measurement now in mind, we have a complete picture of 17 fluorine measured over a wide range of Z. And what I have plotted here is bringing back the universal fusion function with the experimental results of all three systems normalized by what I have shown here. And as you can see above the barrier, which again would be 0 here, the data agrees quite nicely and shows no suppression above the barrier. Again, indicating that the halo-ness of this nucleus, as well as the weakly boundedness of this nucleus, seems to show no special effect in fusion above the barrier. However, some more below barrier measurements might be needed to fully parse that out. So what can we conclude from this? Well, really just that 17 fluorine behaves as it should in above barrier fusion, unlike up until a few days ago, a boron, and unlike neutron halos, which show a pretty clear systematic of breakup in above barrier regions showing suppression. Now that we have a measurement over a large range of Z, I think rules out any sort of polarization effect that might happen with this nucleus. And on top of that, the calculations I showed specifically omit this 1/2 plus excited state and reproduce the total fusion cross-section quite well. So what's next? Well, and as I mentioned at the beginning of the talk, there's still not a lot of data on proton-halo nuclei. As I said, a boron has only been measured three times now, but we still need to understand these nuclei. I think 17 neon is probably the next one, and we will be able to measure these as EFRID comes online. On top of that, I hope I showed that Encore and active targets can play a unique role in measuring the systematics of fusion with these nuclei. And on top of that, at least with Encore, we can fill it up anywhere from helium all the way up to effectively krypton, which could offer some more insight on this charge effect that may or may not happen with these nuclei. And in particular with Encore, there are future improvements aimed to identify specific exit channels. So in the analysis procedure I showed before, we only know that there is an evaporation residue, but not which one it is. And we have since been playing around with measuring drift times and whatnot to essentially get a full track of the evaporation residue as it come out to try to specifically nail down the A and the Z, though this is still in its infancy. So with all that being said, I would like to thank you guys for listening to my talk, and thanks to the NSF for funding my research, and a huge thank you to my research group and the Fox Lab staff here, of which this is only a short list, as well as the Argonne collaborators, and a very special thank you to Nicholas Keeley, who helped in the calculation of the system. Thanks.
Thank you. If anyone has any questions, oh, someone's already raised their hand. I see Ramado. Please go ahead. You can ask your question.
Yes. Hi, Ben. Great seminar, and congratulations on building a really powerful experimental tool. I do have a question, though, about your fluorine-17 data. So as you know, there's another measurement in the preprint server, which using a thin target, actually, so you don't have the issue associated with the energy determination, measures different cross-sections. So you've got the same reaction, and you've got two different sets of cross-sections. Now, of course, one could always claim that I'm right and you're wrong, right? But how do we scientifically go about resolving the issue? And in answering the question, I wonder if it's helpful to think about something that you actually brought up in your seminar, which is that you can think about the fluorine-17 as a system consisting of an O16 core and a proton. So is there another reference system you might think about that could provide you, from the viewpoint of data, an appropriate reference measurement?
For 17 fluorine specifically?
For fluorine-17, yeah.
Well, it would be 19 fluorine, which I also measured within my detector using the same analysis and the same systematics, essentially.
Well, but 19 fluorine, you see.
Could I interrupt? This is Kirby Kemper. If you plot the preprint data with Ben's data, there are only 2 points that are different. So I hate to disagree with Romaldo, but we have done that. And in fact, there are only 2 points that are different.
Well, Kirby, I hate to disagree with you, but.
Well, I understand that.
Yeah, and I could tell you that, let's imagine you think of the mirror nucleus, oxygen 17.
Right.
Yep.
They want to flip that halo, but that valence.
Well, we've also measured that, though that's outside of the scope of this talk, and I'm not allowed to show the results of that.
Well, so you can compare with the literature values, the fluorine-17 with.
Well, they don't. The literature values have a huge discrepancy in them.
And I think we will show that you can understand that discrepancy perfectly.
Okay.
Probably this is out of the scope of this talk, right? So probably we can continue with some other questions.
And we're all excited to see those data, especially when they're finally published. So that's exciting. Any other questions or comments? You still got your hand up, Ramado? Do you want to put the hand down? Oh, yeah, I'm just checking. I had a couple of questions. One was about the left-right plane as your beam goes through. Do you find you have a lot of sensitivity to the beam tuning? If the and do you actually use this in the process of focusing your beam?
No. So with the silicon detector in the back, and also with the gas window, which is I can't remember the size of it off the top of my head, but it's actually smaller than this staggering. And on top of that, we have collimators, since we can't pump a lot of beam into this upstream. So the beam profile is very well understood as it passes through the detector. In principle, though, yeah, we could sort of try to bend it left and right, but it's pretty well focused.
Okay, and what is the separation left-right compared to like the width of the beam you're dealing with?
Well, the staggering here is about 2 centimeters, I believe.
Oh, okay.
And the straggling of the beam, I don't know off the top of my head. But one way to really look at that is with this, what I have shown in front of you, and that even with the thickness of the beam, it still stays right in the middle.
Right, yeah. I guess probably a centimeter or so would be reasonable with a in-flight beam of this kind. But maybe someone else has something to say. Does anyone else have any question? You can put questions in the chat as well. Ramado, do you have something else?
Yeah, one slight comment. So Ben, you made the in your introduction a pretty thorough description of thin target versus thick target, but you made a couple of statements that really aren't quite accurate. So you talked about the problem of efficiency with, for example, an energy time of flight approach, which we've used in the Indiana group for several years.
No, what I really was trying to say was, as we push away from stability, that the use, what I was trying to say was the efficiency of the use of your beam time, meaning as you're awarded beam time.
Yeah, that's perfect. I completely agree with that. But my question is actually a little bit different. So the question is, I agree with you, the thick target approach, the active TPC or active target approach is really effective for measuring the cross section. What is it you give up?
Well, we only measure total fusion, if that's what you mean.
Yeah, so there's information about perhaps about channels or
right, and that's aimed at the future of this detector, really. Since we've been playing around with some of the drift times, we're starting to get a little bit of a handle on being able to really nail down the A and the Z of the exit channels.
Yeah, that's a powerful information to get.
I see Lisa Butka has his hand up. If you want to go ahead and ask a question, Lee. Are you there, Lee? I don't hear him. He did make a comment in the chat about music detectors. The first one that he's aware of and that I'm aware of was from GSI.
Oh, right. Yeah, I probably should have mentioned it's the one at Argonne is not the first one. I didn't mean to imply that.
I guess it's the one you based yours off of.
Right.
Right. Are you there, Lee? This is where I go into seance mode. Okay, are you hearing me? Oh, his mic is not working. Do you want to type in your chat then, and I'll read out your question? we're just waiting for Lee to type his question. If anyone else has any questions. Oh, is the reason to use music instead of a TPC? Is the reason to use music instead of a TPC rate?
Oh, that's a good question. Sorry, I was just reading his question myself. I really haven't thought about it since, as I mentioned before, as far as I know, the only fusion measurement that's been done with a TPC was the TechSat detector, which just published their results. So I know TPCs, I think in general, can have more rate in them, if that's what you mean.
No.
It's the reverse.
Oh, well, again, I'm not super familiar with TPCs in general. So in that case, yes.
Okay, and Ramada says unnecessary complexity in TPC if you just want to get the fusion cross-section. Yeah, I guess I'll read out limitations. So a TPC would give you the kinematics, the actual tracks of the products, right? Rather than just a Bragg curve.
Right.
Okay. I have a layman question as a non-nuclear guy. Yeah, this is from Dave Fink. Do you want to go ahead? Do you want to unmute yourself?
Dave, you can come up here and ask me, man.
Oh, you don't have a mic that works. Do you want to continue typing there? Oh, when you say the gas is quenched, what do you mean?
Oh, so there's this kind of weird effect if you were just to have stale gas in the detector, as you shoot more and more beam into it, your signals become weaker and weaker. I don't really have the greatest explanation as to why this happens, other than I have seen it happen. So basically, you just keep fresh gas in to make sure you have the best looking signals.
Yeah, we've seen this in ionization chambers that you need to circulate the gas.
Right.
Sometimes, in some situations, you can keep the gas there for a little while. Sometimes.
Hi, can you hear me now? This is Lee.
Yes.
We can hear you now, Lee.
Thank
I hear you loud and clear.
I'm sorry, I had to get off and get back on. It happens to me every now and again. The world, my computer as well as the world, I guess, gets tired of listening to me. So, in the astrophysical setting, I understand the reason to look at neutron-rich species. They may power, I guess it may power X-ray bursts or something. What is the astrophysical interest on the proton-rich side?
Well, in this case, I wasn't really looking at an astrophysical sense. It was more of just, again, to try to complete the picture, since on the neutron side, there is this breakup as it happens. And since there hasn't been any measurements, or not very many measurements on the proton side, we wanted to see if this was also the case.
So, to anyone, is there an astrophysical interest on the proton-rich side? Does it power any?
For fusion, I don't think so, right?
Mostly alpha.
It's mostly
sure. I'm not talking
alpha
about,
P or all the type of reaction. For fusion is limited.
Yeah, no, I'm not talking about RP. I'm talking about heavy element, not light fusion, astrophysical. And the answer is no.
Probably not.
Okay, thank you. I happen to, probably there's a couple other people who were around when Han San built his massive TPC, his massive music that he brought to various places around the world, including Berkeley, when they were doing secondary beam stuff. And it was music you could walk into.
Oh, and Dave Morrissey says, fuel gas gets radiation damage, particularly with heavy ions. Gas quenching relies on additional small molecules in an atomic noble gas filling, an atomic noble gas filling to de-excite the high-lying metastable states. So thank you, Dave, for the explanation there.
Sure, thanks. And just to finish, I mean, the GSI people are still using music chambers in their fragment separator. And I think Lee was right about the rate in the TPC. You have to drift the ions along the path, and you have to process all the signals, so you get a rate limit.
You don't have to drift them a lot. You don't have to drift them along the path. You can drift them transverse.
Yeah, but nobody does that, do they?
Yes. They're not. What do we call them? You know, they're not Bragg. They're not Bragg curved by design. They're transverse by design.
Sure, I understand.
I'm not an expert in PPCs by any means, but I would think that because you have much higher segmentation, therefore your primary ionization is over a given segment is less. You then have the amplification of the gem, and so your energy resolution, in fact, can't be as good as if you just collect the primary ionization over a larger segment.
Well, I'm not sure about that. There may or may not be true, but one of the problems, one of the questions that I was going to ask Ben earlier was when he was comparing the calculations, he was comparing his, which had a broad horizontal error bar, to a calculation which looked like it was not. I didn't know. And so the question, were they also averaged over the same horizontal bin? In which case, if they weren't, it was apples and orange comparison. Below barrier, above barrier doesn't matter. But you know, as you approach the barrier, how you do that averaging varies very much with a broad sampling energy device like the music.
Right. That's kind of why this the talk is mostly just about above barrier, since of course as we go below, you need to really understand the energy down there. But
can you do better than?
That's why I brought it up, Romaldo, because that's where the TPC would be better, because it doesn't average over so much. Yes.
So let me ask the question in a slightly different way. Ben, can you at present you're just showing us as your horizontal error bar the energy width of a given anode, I suppose.
yes.
Yeah. So do you have any hope or plans or anything to actually reduce the error bar from that value?
Well, I mean, the easiest way is just to decrease your pressure. We also have been playing with ideas of different anode shapes, since you can decrease the thickness of that, but that's the primary ways of doing it.
But in both of those cases, you effectively reduce the amount of your signal. So you can't, you can reduce your pressure. Maybe you can go 50% down or something like that. You can't go to 1/10 the pressure.
No, not that low.
Yeah.
No.
So what's the limit then on your reduction in the error bar you can?
Probably maybe almost let's see. We've operated at as low as 80 torr. I can't remember off the top of my head what beam it was though. So probably at least by half.
Mm-hmm. But I guess the issue with the TPC is just the amount of data you get. You're kind of rate limited unless you can take a lot more data.
Well, on another front, Kate, I don't think you'd argue against DSP, using DSP, and that's a data swamp. So we're getting better and better at dealing with large data. By the way, Ben, when San came out with his, and other people were building their TPCs in the 70s, don't know if you've dug into the history, but there was a lot of different anode. There was a lot of different anode designs.
Yeah.
And, you know, they sawtooth, which those of us that were growing up in that era we're calling the Rosner anode, because that's the guy that built the first one of that sawtooth type. But there was lots of different anode arrangements that were played with. And so there's a long history of that. The sawtooth one, when I saw it first in the 70s, oh, that's clever. So, but anyway.
Thanks, Lee. Okay, if no one else has
I
any...
have a comment.
Oh, you do?
Sorry to interrupt. I was looking for the raised hand, but I couldn't find it. This is Melina. Just a comment about the TPC and music, in my opinion, but I need to check. I think if you build, I mean, in principle, you can go from ionization chamber to TPC, or what I mean is with using the same segmentation of music, you can build a TPC. There should be no problem. So in real, well, I think the issue is not if it's a TPC or a ionization chamber. It's what is the segmentation that you have. If you build a TPC with the similar segmentation that music, I think you remove the issues of having like a lot of data and all that was being discussed. Sorry, that's it.
No, thank you.
Was just a comment.
Okay. Any other questions or comments? If not, I'd like to thank Ben again for a very nice talk. And Ben should be graduating in the summer and is looking for a position. So please contact him if you're interested. And thank you all for coming.
Yeah, thanks everybody. And happy opening day to anyone who's a baseball fan.
Bye then.
Thanks, Ben. Very nice talk.
Thanks.